In the movie Mission to Mars, there is a scene where one of the characters, while in space, removes the helmet and literally seconds later turns into an ice sculpture. That scene is very dramatic and completely inaccurate. The plot device of someone instantly freezing in space without a spacesuit, along with similar inaccuracies, is not uncommon in the movies. And it's understandable why. We usually think of space as being cold. Someone might say that the temperature in space is close to absolute zero. Although the phrase temperature of space itself is not very accurate. And what's wrong here, and is space really cold? If we want to delve into this more deeply, it won't just come down to heat transfer and all that. We'll even have to touch on the birth of the universe itself. So would we really freeze in open space? How is the temperature controlled for astronauts? What are the conditions in the solar system, interstellar space, and intergalactic space? And why is intergalactic gas so hot? How can cosmic microwave background radiation have a temperature, and what is the temperature of the universe? And also, what does the James Webb Space Telescope have to do with all this? Today we'll discuss all this and much more, and my name is Andrei, and this is Cosmos Elementary. So, how cold is space? What is its temperature? Okay, to even attempt to answer this question similar to my previous video where we discussed whether time exists, we first had to clarify what we mean by the words time and exists. Similarly, here we need to specify what we mean by the words space and temperature. What is space? Usually we refer to everything above the Kármán line or 100 kilometers or about 62 miles above Earth as space. However, this is just an arbitrary altitude. At an altitude of 30 kilometers or 18.5 miles, the Earth's atmospheric density is only 1.5% of sea level air density. Here is a video from such an altitude taken from a weather balloon, which, by the way, I launched with my own hands. So it already looks like space. On the other hand, the very thin atmosphere continues for hundreds and even thousands of miles upward. The International Space Station and the Hubble Space Telescope are essentially located within the upper layers of the Earth's atmosphere, specifically in the thermosphere. While it's nearly a vacuum for us, there is enough material there to gradually slow the space station down. This causes the station to lose altitude by approximately 2 kilometers per year, and it would eventually deorbit if engines didn't turn on from time to time to raise the station. But that's only in our immediate vicinity, and the space is vast and conditions there can vary greatly. So when asking if it's cold in space, we need to specify where in space. On a low Earth orbit, near Mercury or Neptune, in interstellar space, in an intergalactic void. In each case, the situation would be different. Next, we need to clarify what we mean by the phrase space is cold. I often see online statements like, the temperature of space is minus 270 degrees Celsius, or something like that. The temperature of what? In our everyday lives, we think of temperature as a measure of how hot or cold something is. But more precisely, it is a measure that describes the average amount of kinetic energy in a system. If we're talking about a gas, then it's the speed of the particles, atoms or molecules that make up the gas. The higher the temperature, the faster the particles move, and consequently, the greater kinetic energy they possess. It's an average value because in a given volume of gas, the speed of different particles will always vary. If we're talking about solid objects, the particles don't move freely, instead they sit still in a crystalline lattice. However, the particles can vibrate. Once again, the higher the temperature, the stronger and faster these vibrations, and consequently, the higher the kinetic energy. When we heat a solid object whose particle movement is restricted and it reaches a certain temperature, it melts, transforming into a liquid state where particles move more freely. Further raising the temperature turns it into a gaseous state where particles move even faster and have more freedom. And here the issue of discussing the temperature of space becomes evident. by definition, temperature is a property of matter. When we talk about, for instance, the temperature of air, it's clear. Although we cannot see it, we can clearly feel it just by simply waving our hands very quickly. We are surrounded by a lot of material. But in space, it's almost a vacuum. The key word is almost. Even in the most empty regions in the universe, there is still some minimum amount of particles per volume of space. Therefore, when talking about how cold it is in space, we naturally aren't referring to the temperature of empty space. That would be meaningless. Here we're either talking about the temperature of the matter that does exist in space, or we could discuss the temperature that an object placed in that region of space would ultimately reach. This can be influenced not only by the matter present, but also by radiation. When people talk about the temperature of the universe, they usually mean the temperature of the cosmic microwave background radiation. But how can radiation have temperature when we just mentioned that it is a property of matter? We'll talk about that a little later in the video. It's quite possible that in certain regions of space, without a spacesuit, not only we wouldn't freeze, but we might actually warm up. But even here, it's not entirely straightforward. You may have heard that the temperature of intergalactic gas can reach millions of degrees. However, if some mischievous representative of an advanced alien civilization decided to play a prank on you and teleported you right into the middle of the intergalactic medium, the temperature of that gas would probably be the least of your concerns. What's the problem with conspiracy theorists? They often take a fragment of genuinely accurate information and then, without context and without knowing or even wanting to know the whole story, they make incorrect conclusions. The most ironic aspect is that they often deny official science and say that scientists lie all the time, but the piece of information that seemingly confirmed their point of view and which they used to make incorrect conclusions, where did they take it from? Right, from those very scientists. So in their logic, most scientists do lie, but in this specific instance, they're telling the truth. Convenient. Exactly the same thing happens with the argument of conspiracy theorists about the Earth's thermosphere. The thermosphere is one of the upper layers of our atmosphere, which begins at an altitude of approximately 90 kilometers or 56 miles and extends for hundreds of kilometers beyond that. A distinctive feature of this layer is a very high temperature of the gas, ranging from 500 to 2000 degrees Celsius or 3600 Fahrenheit. And I've already mentioned that the International Space Station, the Hubble Space Telescope and many other satellites are located inside the thermosphere. So, what conclusion do conspiracy theorists make? They think that since there is such a high temperature in the thermosphere, the ISS and Hubble should melt. Therefore, according to their logic, neither of them exists. Astronauts are filmed on movie sets, Hubble images are fake, and space itself doesn't exist, and scientists are hiding the truth. And they got information about the temperature again from scientists. And it is true that temperature there is high. However, for some reason conspiracy theorists ignore or don't know that temperature and heat are not the same thing. And also how heat transfer works and that there are different types of heat transfer. If temperature is a measure of kinetic energy or the speed of particles and it's measured in Kelvin, degrees Celsius, Fahrenheit, then heat is thermal energy transferred from one object to another or from the environment to an object and so on. It is measured in joules. The amount of energy that can be transferred to an object depends not only on the temperature of the surroundings or another object, but also on its properties. Suppose I have a bowl that is at the room temperature, and also I have two containers, one with air and another one with water. And both are at the same temperature of 90 degrees Celsius. Where do you think the bowl will heat up faster? In air or in water? Another example is that many people can sit in a sauna or steam room for an extended period of time, where the temperature can be as high as 90 degrees Celsius or almost 200 Fahrenheit. However, even touching for a split second, water at the same temperature can feel unbearably hot. The temperature is the same, right? But the difference lies in density. Simply put, in a denser medium, the object comes into contact with more particles and gets more energy from them in the same amount of time. In the thermosphere, the density is very low. There are very few particles. Sure, although their speed is high, but the total amount of energy they can transfer to the International Space Station is small, so it would take a very long time due to the extremely low particle count to significantly heat it up through the interaction with gas particles. From the temperature regulation perspective, the International Space Station is more affected by solar radiation. Nonetheless, the station can regulate its temperature using special systems. A more extreme example of that would be Parker's solar probe. There is a so-called coronal heating problem. The problem lies in the fact that the surface temperature of the Sun is approximately 5,500 degrees Celsius, while the temperature of the upper layer of the solar atmosphere, the corona, can reach millions of degrees. The exact mechanism of heating is still unknown, although there are some good ideas and recent developments. So the Parker Solar Probe literally passes through the solar corona, and the temperature of the surrounding matter can reach 1,000,000 degrees. However, due to the low density of this matter and the highly effective cooling system and heat shield, the spacecraft itself doesn't reach such temperatures and remains undamaged. On the one hand, we have the prejudice that space is cold. On the other hand, we read that in the thermosphere, the temperature reaches 2,000 degrees. And we might think that if we go for a spacewalk outside the International Space Station without a spacesuit, such a temperature should cook us. So we already understand that we shouldn't get cooked. But besides the very sparse atmosphere and particles and high speeds, there are other factors. We can not only absorb heat, but also lose it. Let's go back to our instantly freezing body in space. This won't happen quickly, either near the Sun or anywhere else. Here, it's worth reminding about types of heat transfer. Heat can be transferred in several ways. Firstly, there is conduction, where thermal energy is transferred from one molecule to another through direct contact. This type is typical for solids, but not exclusive to them. We experience it when we accidentally grab something hot. Next is convection. Here, heat is transferred along with the movement of mass, typically some kind of fluid. For example, a stream of hot liquid carries heat to an area with cooler liquid. And finally, there is thermal radiation, the transfer of heat through electromagnetic radiation. The heat we feel from the sun, the warmth from bright lamps, and so on, are examples of thermal radiation. The key distinction of this type is that it doesn't require a medium to transfer heat. It can occur through a vacuum. Here is a simple illustration where we can see all three types of heat transfer happening simultaneously. Conduction from the handle to the hand, convection in the water inside the pot, and radiation from the heating element. So what happens when we are in open space? Essentially, 2 out of 3 types of heat transfer won't work there: conduction and convection. Only radiation remains. This means that our body that still has internal heat will not lose it so quickly. Our bodies are essentially like light bulbs, but we emit not visible but infrared light, which is clearly visible on thermal cameras. Naturally, we lose energy this way, but it will happen much more slowly than when other types of heat transfer are also involved. Even if we find ourselves in the coldest region of space, far from the intense radiation of stars, even there, we wouldn't freeze instantly. I've come across some estimates that it could take up to 26 hours for this to happen. But hanging out in space outside the space station under the sunlight, we might not just avoid feeling cold, we could even feel warm there. If you stay constantly in the sunlight, you might not freeze at all. Sure, we would likely faint in a couple dozens of seconds and then die in a couple of minutes because of brain hypoxia, but not get frozen. With specific temperatures, the ISS can provide us with some insights. The primary factor here is the sun. Again, that stereotype that space should be cold beyond the dense layer of the atmosphere. The atmosphere blocks a significant portion of radiation, and not all of it reaches the Earth's surface. Additionally, the atmosphere prevents heat from escaping rapidly back into space. At the altitude of the International Space Station, almost all of the sun's radiation reaches the object. But there's also much more significant temperature variations. Without special thermal regulation systems, areas of the space station directly exposed to the sun can heat up to 121 degrees Celsius, while those in shadow can cool down to as low as minus 157 degrees Celsius. Therefore, to maintain a moderate temperature inside, insulation is required. However, this insulation is different from what is used on Earth. In an environment where radiation is the dominant form of heat transfer, a significant emphasis is placed on reflective surfaces. Also, a liquid cooling system and large radiators help dissipate excess heat. By the way, assuming the space is cold, one might think that spacesuits for extravehicular activities must have a way to keep a person warm inside. However, it's the opposite. Cooling systems are in place to get rid of excess heat. Well, if we ended up in open space without a spacesuit, at the same distance from the sun as Earth, and by some chance we were constantly in shadow, then eventually our bodies would freeze. But under the constant sunlight, we would even warm up, especially the side that is facing the sun. And for the most efficient heat distribution, we would need to spin. That's near Earth. But what about the rest of the solar system? Well, it's more or less straightforward. The principle is the same, but the intensity of solar radiation varies. The closer to the sun, the more intense the radiation, and the farther away, the weaker it becomes. There are many factors at play here, like properties of the object and how it reflects or absorbs solar radiation. Our thermosphere is so hot because the sparse gas in the atmosphere effectively absorbs ultraviolet and other types of radiation, heating it up significantly. The heat shield of the Parker Solar Probe is designed to reflect radiation, yet it still heats up to 1400 degrees Celsius. The surface of the closest planet to the Sun, Mercury, where there is virtually no atmosphere, heats up to 430 degrees Celsius or about 800 Fahrenheit in the sunlight, and can drop to minus 180 degrees Celsius in the shadow. If we return closer to Earth, a great example is the James Webb Space Telescope. Why is this a good example? Because temperature is especially crucial for this instrument. It operates in the infrared range. To achieve maximum efficiency and sensitivity, its instruments must be very cold. Some need to be cooled down to a temperature as low as 7 Kelvin, which is minus 266 degrees Celsius, very close to absolute zero. And what's interesting is that even in space, quite far from Earth, at a distance of 1.5 million kilometers or 930,000 miles, its instruments wouldn't naturally reach such low temperatures on their own. Therefore, it has a cooling system that consists of two parts. There is passive cooling. As we have already determined, the primary heat source in the solar system is the sun, so it's evident that if we want to cool the instruments down, we need to shield them from the sun. The main element of the telescope's design intended for this purpose is a multi-layered thermal screen the size of a tennis court. Some instruments can be passively cooled down this way to 37 Kelvin. This process of passive cooling takes quite a long time. However, to bring some instruments down to the desired 7 Kelvin, active cooling is required. Essentially, the active cooling system is an advanced refrigerator that uses helium, pumps, and operates in multiple stages. In short, even in space, it's not cold enough, and the entire process takes months. And this is at approximately the same distance from the Sun as Earth. If we go farther from the Sun to the distance of Mars orbit, we can look not at Mars itself, which has at least some atmosphere, but, for example, at its moon Phobos. The temperature there can reach up to minus 4 degrees Celsius. However, once again, the Sun is not the sole factor. For example, heat may be lost because dust of Phobos doesn't efficiently retain it. Minimum temperatures on Phobos can reach minus 112 degrees Celsius. It may seem strange that on Mercury, which is much closer to the Sun, it can get much colder, reaching minus 180 degrees Celsius. But, as I mentioned, distance is not the only factor. Mercury rotates very slowly on its axis. What we would call a day on Mercury lasts 176 Earth days. That means a night on Mercury lasts many Earth months, and areas in the shadow can cool down to the very low temperatures during this time, and there is no atmosphere that could somehow retain heat. And if a body rotates faster with fewer of its areas in shadow at once, even if a body is farther from the Sun, it may not cool down to the same extent. But let's go farther away, let's say to Pluto. From its surface, the Sun already appears as very bright, well, the brightest star in the sky. Here on the surface, the warmest one can hope for is 55 Kelvin or minus 218 degrees Celsius. Meanwhile, the coldest is about 33 Kelvin. If we go beyond the solar system, conditions can again vary significantly. One of the coldest regions is molecular clouds. Again, it is clear that we are talking about specifically the temperature of the matter there. Molecular clouds are the very regions where stars form. They are called molecular because conditions there allow molecules to form, primarily hydrogen molecules. These are the coldest and the densest concentrations of matter. The temperature there is around 10 Kelvin. With a slight increase in temperature, hydrogen molecules break apart into individual atoms. However, the high content of dust helps shield the gas from the impact of light, keeping the gas so cold. The dust forms a kind of a natural thermal shield. In atomic hydrogen clouds, the temperature is somewhat higher, around 100 Kelvin. Clouds around powerful sources of radiation, such as stars and young stellar remnants, places like planetary nebulae, can be quite hot, reaching temperatures of 10,000 degrees Celsius. And it's no secret that matter around supermassive black holes can be heated to millions and millions of degrees. In general, the situation is somewhat similar everywhere. Close to a radiation source, matter heats up. Far away from it, it remains cold, and even in the coldest regions, we wouldn't freeze instantly. And in some places that we would consider space, we wouldn't freeze at all. There's also gas in intergalactic space, which surprisingly is very hot. The temperature of this gas can reach millions of degrees. However, we remember that the temperature of gas is, roughly speaking, the speed of its particles. The density of such gas is extremely low. In 1 cubic meter of space, there may be less than 1 atom. Atoms there almost never collide and do not slow down. Magnetic fields, galactic activity, and other factors may also be involved in these regions. And again, with such a low density, a seemingly immense temperature shouldn't frighten us that much. But what is the coldest place in space? Well, we already established that the empty space itself doesn't have a temperature. And we can talk about temperature of some substance. Plus, temperature is not the only thing we care about. But as we know, the theoretical limit is absolute zero. 0 Kelvin, or minus 273.15 degrees Celsius. The temperature at which a system reaches the state of minimum possible energy. All particles must come to a complete stop. In practice, achieving absolute zero is impossible, partially because of quantum effects. Particles still exhibit some movement. In lab experiments, temperatures close to absolute zero are reached, but that's the extent of it. Sometimes you may hear that the temperature of the universe is 2.725 Kelvin, or almost 3 Kelvin, above absolute zero. And that is the current temperature of the cosmic microwave background radiation. But I just mentioned that temperature is a property of matter. So what's this radiation temperature all about, and why sometimes it is referred to as the temperature of the universe? I have already talked about the cosmic microwave background radiation, or CMB, and even made a video almost entirely dedicated to it. This is the earliest light of the universe that we are capable of detecting. It is also referred to as the echo of the Big Bang. According to the prevailing modern theory, the universe originated from the Big Bang. During the early stages of expansion, the universe was extremely dense and hot. It was at this time that one could indeed talk about the temperature of the universe, roughly in the same context as we discussed the temperature of water or air. After all, there were much more particles, mostly subatomic particles, contained in a certain volume of space. It was so dense that during the first 380,000 years of the universe's existence, it was opaque. It was like a hot cosmic fog or a soup of particles and radiation. However, 380,000 years after the expansion started, the universe expanded sufficiently and cooled down enough so the photons, which previously were constantly scattered, absorbed and re-emitted by matter, could finally traverse large distances without regularly colliding with particles of matter. Distances so vast that we still detect those photons, and the photons that have been traveling through the universe for almost 13.8 billion years are still reaching us. So that is the cosmic microwave background radiation. Due to the expansion of the universe, as these photons traveled, their wavelengths got stretched. Originally they were visible light, and now it is in the form of microwave radiation. We cannot see it with our eyes, but we can detect it with specialized detectors. We are, in a sense, situated at the center of a bubble, the surface of which is the last scattering surface, the region of space from which the photons of the cosmic microwave background radiation currently reaching us originated. Every moment, photons from increasingly distant regions are reaching us. The entire universe is filled with these photons of CMB. They are everywhere, even in the emptiest regions of the universe. And it is said that the temperature of this radiation today is 2.725 Kelvin. But what does that mean? Radiation can be thermal or non-thermal. Thermal radiation is electromagnetic radiation emitted by a substance whose temperature is above absolute zero. In essence, this includes all matter. The properties of this radiation depend directly on the temperature of matter. There is not only thermal radiation. Laser radiation, for instance, is non-thermal. And in astronomy, for example, there is a synchrotron radiation. We won't delve into the details of that at the moment. The crucial point is that thermal radiation has a very characteristic spectrum, and through it we can see that temperature is directly related to properties of radiation. In the case of cosmic microwave background radiation, it is indeed thermal in nature. What is so special about this spectrum? Here it's worth mentioning the concept of the perfect black body. It is a theoretical model of an object that absorbs all incoming radiation and reflects nothing back. And at the same time, it can emit radiation itself. It is a perfect absorber and perfect emitter. The perfect black body doesn't exist in reality. However, if it did exist, all of the radiation we would register from it would depend only on its temperature. So the temperature of the body is a crucial parameter for radiation. The spectra of black bodies look like this. While there is no perfect black body, the spectra of many objects closely resemble the spectra of a perfect black body. A good example is stars. Stars do not reflect radiation, but they do emit it. If we take sunlight, for example, pass it through a prism, break it down into a spectrum, and plot the wavelength distribution on a graph, we get a pattern close to the curve of a perfect black body. We look at the wavelengths present in the resulting spectrum and measure the intensity of waves of different wavelengths. On this graph we have wavelengths on the horizontal axis and intensity on the vertical axis. This visual representation allows us to clearly see what kind of radiation the sun emits, and it indicates which radiation is the strongest. And this peak on the graph and the distribution of wavelengths depend on the temperature of the star's surface. By the way, this is an interactive graph, and here's the spectrum of the sun. Interestingly, the peak of the sun's spectrum is in the green region, yet the overall radiation we observe is more akin to white. If we set the temperature to that of a red dwarf and for better visibility scale up the graph, we will see that the peak is actually in the infrared range. Visually, we perceive the light as reddish. If we set the temperature to that of more massive and hotter star like Sirius A, then the peak is in the ultraviolet range. Visually, the star appears blue to us. Emission and color indeed depend on temperature. We can clearly see that in images like this one of the spectral classification of stars, which range from red, indicating cooler temperature, to blue, indicating hotter temperatures. A metal heated to different temperatures is also a good visual representation of that. The lower the temperature, the redder the color. And the hotter it gets, the closer it gets to white. So what I'm getting at is that the spectrum of cosmic microwave background radiation indeed has a characteristic shape of a spectrum of black body. Very close to a perfect black body. CMB has been measured at various wavelengths within the microwave range. And if we plot them on a graph similar to what we did with the Sun, the scale on this graph won't be enough though. But in general, if we perform the same procedure and conduct calculations using the same formulas, which is done automatically in this interactive model when I simply move the slider, we will see that the spectrum of cosmic microwave background radiation corresponds to a temperature of 2.725 Kelvin. In the same way, the spectrum of solar radiation corresponds to a temperature of approximately 5800 Kelvin. If we consider that the waves have been stretching for over 13.8 billion years of the universe's expansion, we can calculate that initially this radiation corresponded to a temperature of approximately 3000 Kelvin or 2726 degrees Celsius. This information is in the visible range, and just before becoming transparent, the universe was a kind of a orangish soup of particles and radiation in thermodynamic equilibrium. If we take an object, place it in the farthest region of some cosmic void, shield it somehow from all other sources like starlight, gas, and so on, then gradually our object should reach thermal equilibrium with the surroundings. If it was warmer, the object would cool down to 2.725 Kelvin, and if it were cooler, CMB would heat it up to that temperature. One might think that this should be the minimum temperature in the universe. But as I mentioned, in laboratories we can artificially cool substances even further, again through active cooling methods. It's interesting to note that cooling below the temperature of CMB can also occur naturally. Currently, the Boomerang Nebula is the only known place in the universe where natural cooling below the temperature of CMB occurs. When scientists observed it, they noticed that the material there absorbs CMB, indicating that it must be even colder there. The temperature is estimated to be around 1 Kelvin, very close to absolute zero. It's hard to pinpoint the exact reason for this phenomenon, but it's likely associated with very fast flows of cold material, possibly from a binary star system. Astronomers draw an analogy here with a refrigerator, which removes thermal energy from a certain area. In any case, this cooling won't last long, and the processes that cool matter there will eventually stop. The material will then heat up, at least to the temperature of CMB. It's actually already warming up. To sum up, everywhere humans have been in space so far, we can actually not freeze but warm up, as long as we are not constantly shielded from the sunlight. Also, it's not correct to talk about the temperature of space itself. It's more appropriate to discuss the temperature of matter and radiation in space. Conditions in the universe vary significantly, and in some places an object may heat up and even melt, while in others it may freeze. Even in regions far from stars, these processes don't happen instantly, but rather occur gradually. At some point, the universe was indeed a very hot place everywhere. The temperature associated with cosmic microwave background radiation, which is around 2.725 Kelvin now, will continue to decrease further. Current temperature is not the limit, and the universe doesn't seem to stop expanding. Thanks for watching. Links to all of the sources are, as usual, down below in the description. And if you enjoyed the video, leave a like, comment, subscribe, and feel free to share this video with your friends. Bye!